What up, athletes? Woo woo! All right, it is 9.4.2. And today I would recommend having at least a pencil and a highlighter, as well as a straight edge of some kind. And I'm going to also have a pen to that mix. You know what I'm saying? I like to do things. A lot going on at one time. So, let me get my crumbs off the paper. I was eating a delicious snickerdoodle. It's my favorite cookie. Drink that with coffee. That's a match made in heaven. You know what I'm saying? All right. So our EQ today is, how can I apply it? How can I apply inequalities? Okay. So we've been doing a lot with linear and quadratic equations with inequalities, and we've been finding out solution regions. But now what I really want to get into is, how is this even useful? Because this is one of my favorite types of math, because this is math that's really used. We're going to do a simplified version of it, but basically this is how triangulation works, right? Equations and algorithms use this type of an idea to triangulate where people are. And we're going to talk about that. We're going to do a search and rescue problem today, titled Search and Rescue. So without further ado, take a minute. Go ahead and pause this. I want you to read through it, and I want you to highlight anything you think is important. And I want you to read up here the problem, but also read the different accounts from different people, and just highlight what you think, or underline, or whatever, the important information in this. So I'll do it while on pause. All right. Make sure you read that. Go ahead and read the basic facts of the case, the pilot's report of a plane nearby, and the phone call received today. All right. You may wonder, Mr. Tim, why are you just sitting here reading it with us? Because, I mean, you got to read it, I got to read it, right? Make sure to underline, highlight everything you think is important. All right. You can pause right now, because I'm going to go ahead and go off and talk about a little bit about what we're doing here. So if you need to finish, go ahead and pause. Okay, and here we go. I'm completely lost, water everywhere I can see. Both burners have failed. Wait, I see land. I'm going to try to land. I think it's... Those were the last words heard from Harold and his hot air balloon. The last time the balloon showed up on radar, it was near the Solomon Islands in the Pacific Ocean. So what did I do? I went ahead and circled Solomon Islands on my map, because that's where it was near, right? That might help us later. Your task is to determine where to send the search and rescue teams. Use the following reports along with the map, and look carefully for information that will help you draw constraints on where the balloon might be found. Give the search constraints as a system of inequalities. Be sure to identify the probable landing site on the map. Click on the lower right corner of the graph to view it in full screen. Oh, well, we can't do that clearly because Yours is a printout of the map. So I'm going to go ahead and scroll up because most of our pertinent information is really down here, and that way you can see both the map and this. Again, all I did with the information from the first paragraph was circle the Solomon Islands. I know it's at least somewhere. We were going that direction, but let's find out where we were going from. So let's read the basic facts of the case. The balloon departed from the airport at the very northern tip of the Philippines. So that is right here, northern tip of the Philippines. The flight was supposed to follow a straight path directly to an airport in French Polynesia. So let's look. French Polynesia's down here. Boom. What are we going to do? Let's connect it. Now, I actually need to get a bigger ruler. I understand that some of these lines may be dotted or dashed. For this particular exercise, I'm not too particularly concerned about it. Because, well, you'll see why. We can always go back and label it later, right? So I'm just going to draw solid lines for this. We do want to draw all the way through. And this is the balloon. This is the balloon facts. The balloon departed, so it was supposed to go here. Here's the problem. Are you ready for this? Well, let's just look at this too. Do we have any lattice points we can kind of latch onto? Well, yeah, it passes directly through the y-intercept there, and it's directly through a nice x-intercept there. And if we look at this, let's check this out. Now it's going down, so that's negative, right? And down how many? 2, so that's negative. Now if you look down here, I do want to pay attention to this. It shows that every distance is 1,000 kilometers. So even though this goes down 2, it's really going down minus 2,000. And it's going over to the right, 1, 2, 3, 4, so 4,000. So for Harold's balloon, here's what I now know. I just did a slope triangle, right? And that slope triangle is m equals, what's the rise? Remember, we always do the vertical height up top. It's negative 2,000. Over what? 4,000. Which we can cross those zeros out. It's just negative 2 over 4 or negative 1/2. Now, we're also given our b value, aren't we? Because our b value is just where it crossed through. Excuse me. It is at b equals positive 2,000. Sorry, I had an interruption. So where was I? All right. If you look down here, it's below. So that means it's less than, right? Because if this is the path the balloon was supposed to be taking. So we're talking about the balloon right now, right? The basic facts of the case, the balloon. And this balloon should have traveled this direction. But what did it do? It was last seen the balloon's last known location was negative 1,000. Oh, I'm sorry. It was seen near the Solomon Islands up here, but then we also know its last known location was what? Negative 1,000, 1,000. So here, again, right near the Solomon Islands, right? So we know it's less than. So part of the facts of the case we can put for Harold's balloon, we know that y, I should have wrote this a little better, I'll do better on the pilot, is less than, because wherever Harold's at is less than, what's our m, our slope? Negative 1/2 x. What's our b value? Plus 2,000. See how we were able to create the equation of a line? And since it's less than, what we know is it is somewhere in this bottom half of the graph. All right? I'm just kind of lightly shading it in. And you'll want to lightly shade it in because it's going to get darker and darker as we shade a certain area. You'll see what happens here. Now let's read about the pilot. Pilot's report from nearby plane. We were on our way from Australia when we saw a hot air balloon sinking rapidly. I am certain that it crashed south of our flight path. So again, south is down. Down is. So south is down, which is less than again. So we're doing another less than. When we left Australia, so we left Australia right here. And notice Australia is at a perfect lattice point. What do I mean by lattice point again, guys? See this little grid line? This grid line meets right there, right? This is exactly the point, what? Negative 1, 2, 3, 4. So that's the point, negative 4,000. And down 1, 2, 3, 4. Wait, negative 1, 2, 3. Excuse me. Oh, excuse me, guys. Sorry. That's the point. Negative 3,000, comma, negative 4,000. Okay? And what does it tell us? It says we traveled 2,000 kilometers north, that's up, for every 3,000 kilometers east. That's right. So that means we go up from here. Up 1, 2, over 1, 2, 3. So that's a slope, by the way. So notice we know what our slope is. M equals north. We always do the vertical first. 2,000 over 3,000. So now we have our slope, and what does that equal? Again, zeros cancel out. We're just left with 2/3, and it's positive, right? Because they're going up and over, right? They're going along this path, and we can actually carry that a few more. So up 2 over 1, 2, 3. Up 2 over 1, 2, 3. And it said less than, but again, I told you I'm not really, so this one I know for sure is a dotted line. I'm not too worried about it, but I'm going to make a dash since I know this one ahead of time. That just tells us that wherever that balloon is, it can't be on that line. And don't forget, less than is here and lower, so let's shade in an area here. Then let's talk about what we know. Okay, I now know just with these two lines, it is not anywhere on this top half of the graph, because remember, where the reports meet is where we're going to end up finding Harold. And right now, only one graph is shaded here, so that doesn't work. Only one graph is shaded here. They're both shaded down here. So I already know that he could be in Samoa, Tonga. He might be Vanuatu, I guess, right there. Or no, that's Fiji right there. I'm sorry, New Zealand, French Polynesia, maybe the bottom part of it. He's somewhere in this part of the ocean. So let's also go ahead and take a moment and graph this line. Notice when I did the up 2 over 3, I landed right on a y-intercept. So what's our y-intercept? Remember, each one's worth 1,000. So even though it looks like negative 2, it's really negative 2,000. So our b equals negative 2,000. That means our y, again, we know it's less than, right? We already had that. And what's our slope? 2/3 x minus 2,000. So we had y equals negative 1/2 x plus 2,000. And now we have y equals 2/3 x minus 2,000. Okay? We have one more line to draw from a phone call. I was a passenger on a flight that flew directly from French Polynesia to Indonesia. Well, that sounds important, right? French Polynesia to Indonesia. So let's go ahead and connect those. We've got French Polynesia here already. Where's Indonesia? Indonesia's over here. Okay? So, oh, and let's read just a second. I was looking out my window when I saw the balloon going down to the north of where we were flying. It says to the north, so I know this is going to be greater than. And I'm going to go ahead and make it a dashed line because we know it's greater than. Why not? So we've got Indonesia to French Polynesia. After I draw this line, you guys may be able to really guess pretty easily where it's coming from. And we know that it's going to be greater than, right? So we're going to have a y is greater than on this one. And then greater than what? Well, let's see if we have, it goes right through 0, 0. So we're not going to have a y-intercept. Our b equals 0, right? It's right at the origin there. And pause so I could sneeze right there for a minute. But our b is right at the origin. Let's see if we can find lattice points. Now I'm looking here and I see a lattice point right here and right here. And what does it do? That's negative
1,000. And that's over 1, 2, 3, 4, 5. So over, just draw my slope triangle, 5,000. So we know that our m equals negative 1,000 over 5,000. Which, again, let's cross out and I have negative 1/5. So y is greater than negative 1/5 x. And again, we can put plus 0, but there's no start line. So we have our 3 lines. Let's watch what else we have. So here's our 3 lines we graphed. But it also said, remember, it's greater than, so we got to shade up. And as we're shading, you're going to see a lot of doubles hitting. But really, there's only one area. Does everybody see this nice little triangle right here? Where they're all 3 shaded. And what do we see? What island is right there? The island of Samoa. So what is our landing site, y'all? It is the island of Samoa. If we're in person, we usually do this as more of an activity. But today I just want to walk you through it and show you math has some really awesome applications. And this is the thing. This is how GPS tracking works, right? They take 3 different sources that are each casting a net out in a direction, which is an inequality. And they're finding out where those 3 nets meet. And that gives you the GPS location of maybe your phone. Or in this case, they use it to track down where a person is lost in the ocean. Because an ocean is huge. And if you are not able to find some way to lessen that ocean, there's not enough ships on the planet to cover all that territory. The ocean is ginormous. So it's pretty amazing. Math has some great applications. With that said, you got some homework on back. Do some good graphing, good problems. Remember that absolute value measures distance, which is always positive. Peace out!